Pascal's triangle. Very simple in its design and yet so useful, so many patterns, so many hidden mathematical algorithms are contained within it. So you start with the number 1 and then create rows based on the value above it. There's only one way to get to the next row, and so you're going to find that each outside row is going to be 1, and that works on both sides because there's only one value above it to help you get to the next level. However, once you're past the first couple of rows, you can start to see the iterative process. So there are 2 ways to get to that square, and so that value is 2. And then when you add 1 and 2, there are going to be 3 ways to get to that square, and then so on and so on. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and so on. And this can continue on for a very, very long time, as long as you want to. So again, 1's on the outside. This will become 5, 10, 10, and 5. If you create your own, try doing a 12 or up to 20 row Pascal's triangle, and then you're going to be able to start to see the various patterns that we'll talk about in this video. The other way to think of Pascal's triangle is by terms. So the very top becomes term 0, 0. So that is row 0. The next item will be row 1, term 0, row 1, term 1, row 2, term 0, row 2, term 1, row 2, term 3. And that iterative process continues on to infinity as well. And now let's find a few characteristics of Pascal's method. The first 6 terms of row 25 are as follows. Can you determine the first 6 rows in the next row? Now I probably should have laid this out horizontally. So you have 125, 300, 2300, 12,650, and 53, 130. So the outside of the next row is going to be 1. The next value will be 1 plus 25, which will be 26. The next value will be 25 plus 300, which is 325. The next will be 2600, and then 14,950, 65, 780. So you're continually adding the 2 values above. Now, using Pascal's method, write a formula for each. So we have term 12,5. So term 12,5 is equal to the 2 above it. So if we have term 12,5, you're going to add term 11,4 plus term 11,5. So the subscripts of these 2 will be identical. So term 40, 32, will be term 39, 31 plus term 39, 32. Again, noticing that these 2 values will be the same. And that leaves us with term N1, R1. And so the numbers above that will be T, N, R, plus T, N, R, plus 1. And again, notice that these 2 terms are identical. These 2 terms are 1 apart. And now which row in Pascal's triangle has the sum of its terms equaling to this value? So each row of Pascal's triangle adds up to a value that can be described in terms of a square. So we have the first few rows here. This equals 2 to the 0, 2 to the 1. 1 plus 2 plus 1 is 4, so that's 2 squared. And 1 plus 3 plus 3 plus 1 is 8, which is 2 cubed. So to discover which row has that as its sum, you can divide many times by 2, and you will end up with 2 to the 15. You can also use logs, but the brute force method is probably the most direct and illustrates the power of Pascal's triangle. So coins can be arranged in the shape of an equilateral triangle, and we want to find out the number of coins in triangles with 4, 5, or 6 rows. So looking at this, what they're saying is you can create triangles with coins. And so if I've got one row, of course, I've got 1 coin. If I have a couple rows, I have 3 coins. If I continually add rows, I'm going to get more and more coins. And here we go. Now I've got 10. And if you look at the triangle, I've already illustrated where those numbers live. They're in the 3rd diagonal. So write down the triangle. So those are the triangular numbers. And now in part C, let's relate Pascal's triangle to the number of coins in a triangle with n rows. So we're trying to come up with an algorithm within the triangle. And then we'll use that algorithm in part D to figure out how many coins would be in the 12th row. So if you look at it, you can see that each and every time it happens to be the second term. So we have got term, this is term 0. I should use a different color. Let me use black. This is term 0. This is term 1. This is term 2. Again, 0, 1, and 2, 0, 1, and 2. So in each case, you find the triangular number as the second term. And so if you come up with the algorithm, you're going to find out that the algorithm will be t, or term, n plus 1, and then it's the second term of that row. Okay? And so now if we want to figure out the number of coins in the 12th row, we substitute in 12 for n, and so it becomes the 13th row, the second term, and that value, I will tell you, is 78. And lastly, can we find a relationship between perfect squares and the sums of pairs of entries in Pascal's triangle? So the sums of pairs. So again, I'll direct you to the 3rd diagonal. So our first term here, in and of itself, is a perfect square. But we want pairs of values. So you take that, add those together, and the perfect square is 4. All right, so 2 squared is 4. 3 squared is 9. So where do we find that? Well, 3 plus 6 is 9. The next pair would be 6 plus 10, which is 16, which is 4 squared. And 5 squared, of course, is 25, and you can find it right here, 10 plus 25. So the algorithm you're looking at is for n squared, it's going to be the term n2 plus the next row n plus 1 second term. And that type of algorithm you're going to be able to find all the way throughout Pascal's triangle. I'll write it a little bit nicer here so you can see it clearly. So it's the row, the second term, plus the next row, and the second term. And that's it. Thank you for listening.